So, last class we looked at the structural error and a way to tackle and minimize that error is to use Chebyshev spacing to find your precision points. So, we saw that you can assume a linear relationship between the input angle of the 4 bar and your input variable, then look at transform the output angle of the 4 bar to the output of the variable. So, let us see how we would use this to determine the parameters or the input and output angles for the 4 bar that we have to design. Okay, use of so given a certain function, we will look at how we will apply Chebyshev spacing. This was the geometric construction for Chebyshev spacing, and we will now do an example. Okay, so let us say determine Chebyshev spacing, meaning find the precision points for the design of a 4 bar which should generate the function y equal to 2x square minus 1 in the range 1 and 2, between 1 and 2, where 4 precision points are to be prescribed. Okay. So, what would you do? You need 4 precision points. So, you would have to again draw the inscribe. So, first draw a circle. What would be the diameter of the circle? What would it be proportional to? Yeah, the diameter proportional to delta x equal to xf minus x naught, which is equal to 1. 2 minus 1, 1. So, I draw the circle such that the diameter, this is x naught, this is xf. Okay. Then I have to construct a polygon of sides 8. Two n equal to 8. And you have to construct it. We saw that the angle that you are looking at for the is this angle would be 22.5 degrees. So, this would be the side of the polygon, that would be the. Then using that I can construct the rest of the polygon. I need to construct only half of it. And so, from the diagram I can read off this will be x1. I draw the vertical lines from these other vertices. So this would be x2, this would be x3, and this would be x4. Or I can use the equation, right? I can compute it that way. So from this, from the geometric construction, I get or equation, you could use that as well. I have x0 equal to 1, x1 1.04, x2 1.3. Even if you don't remember the equation, you know how to, from the geometry of this, you can find x1, x2, x3. So x3 equal to 1.69, x4 equal to 1.96, because you may not be able to measure this off that accurately otherwise. So you can use the geometric construction to then set up the equation to find these values. Okay. And xf is 2. Because you are trying to look at error here, you want to have sufficient number of significant figures. You don't want to round off. Ideally, if you can have more significant figures, that's better. Okay. So once I have the values for x, I am given, there's one more thing I need to be given. What would be the range of rotation for the 4 bar? So I am given delta phi, the input angle, and delta psi is 90 degrees. Okay. So the first part is the finding the precision points for this relationship. So now, given the Chebyshev precision points for the function, in terms of x and the, because I could design multiple linkages for this, right, depending on the range that I choose for the input and output links, and the ranges for the input and output link rotations are given as delta phi equal to 60 degrees, delta psi equal to 90 degrees. I want to find phi 12, phi 13, phi 14, right, from the first position. How much do they? So phi 1, phi 2, phi 3, phi 4 will give me this, and correspondingly psi 14. Okay. So far you know how to design if you are given 2, phi 12, phi 13, and say psi 12, psi 13, but theoretically it is possible to design for more number of precision points. You may need other methods to do so, but it is possible. Okay. So to do that, I first need to find, so I am given, I have found the x values, I need to find the corresponding y values to relate then I will relate x to phi and y to psi. Okay. So, how will I find the y values? I am given the function y equal to 2x square minus 1. So, substitute the values of x, substitute into function y equal to 2x square minus 1 to find, substitute x values into this function to find y naught is 1, y1 is 1.16, 2.43, 6.68, and at x equal to 2, y is 7. Okay. So, now I know my delta x equal to 1, my delta y equal to 6, and I am told that delta phi should be 60, delta psi should be 90. So, I can find my scale factors. I am assuming a linear relationship between x and phi, similarly between y and psi. So, I can find my scale factors. Okay. So, I have r phi equal to delta phi by delta x, 60 by 1, r psi equal to delta psi by delta y, which is 90 by 6. So, you are asking if the function has some other a maximum in that interval. Okay. So, we are looking at a linear relationship, right, between x. So, that would not hold. First, we would have to see whether the Chebyshev spacing holds for that kind of. You would probably split it and do it, but no, then we need to know the conditions. Basically, he is asking what are the conditions in which you can use the Chebyshev spacing, because if a maxima like that occurs in between the we do not really talk about, we are talking about a linear relationship. So, the assumption is that, but the linear relationship is between the delta x, the angle, and the I will have to get back to you on what conditions the function should satisfy in order for the Chebyshev spacing to be valid. Okay. So, when you have this, now I can find my phi 1 as r phi into x1 minus x naught plus phi naught, right, because of the linear relationship between x and phi. So, there are two ways to go about this, because we are interested in the change, right, from position 2 to position 1, phi 1 2, phi 1 3, phi 1 4. You could choose phi naught such that phi 1 will be 0, or you can choose phi 1 to be 0 and everything will just be shifted by a certain angle, because you are interested in the difference from the first position. The angular displacements from the first position is what we are interested in. So, you could either choose phi naught to be 0 without any loss of generality, or you can choose phi naught such that phi 1 will be 0. Then whatever you get as phi 2, phi 3, phi 4 will actually be phi 1 2, phi 1 3 and phi 1 4, because you have chosen phi 1 to be 0. Okay. So, that is possible. So, the scale basically just gets shifted, the range does not change. So, I will just, so when you do this, or I can just compute, I can choose phi naught to be 0, okay. Let us say let phi naught equal to 0, then phi 2 will be r phi x2 minus x1 plus phi 1, phi 3 is r phi okay. So, if I say if I choose phi naught equal to 0, I get phi 1 equal to 60 into 1.04 minus 1 plus 0. So, I get phi 1 equal to 2.4 degrees. In this case, I will get similarly, I can evaluate phi 2, phi 3 and phi 4. Okay. If I choose phi 1 equal to 0, then my phi naught is basically minus 2.4 degrees. So, it is just shifted the scale. So, I will get phi 1 equal to 0, phi 2 equal to 16.2 degrees, phi 3 equal to 39, phi 4 equal to 55.2 degrees. The deltas do not change. Okay. So, it is essentially the same linkage starting at a different position. You would synthesize essentially the same linkage in both cases. Okay. And then you can find the corresponding size in a similar manner in order to synthesize the linkage. This gives you the phi, you have to then synthesize the psi. Using the relationship between r psi and y. Okay. So, this is how you use Chebyshev spacing for function generation in order to determine the precision points. Step. So, in analytical linkage synthesis, okay, so far we have looked at graphical methods for synthesis, which as I have said before are intuitive and easier to do, easier to understand, easier to set up. Analytical methods give you more power. So, graphical methods are essentially based, the design that you do, the synthesis that you do is only based on position. So, your design requirements, if it is based on position and orientation, based on displacement basically, because we have not really looked at graphical methods where you involve time derivatives of the displacement. Say I want a linkage where when the input link has a certain velocity, angular velocity, I want the output link to have a certain angular velocity. We did not, that is not something we were able to do with the graphical synthesis. We were able to say, okay, if it attains a certain position, I want the output link to attain a certain other position. So, it was based more on displacements, but in many cases you may want to have a combination of displacement, velocity, acceleration, only velocity, acceleration, you are involving time derivatives. You may want to involve the transmission angle in the design. You want a linkage that satisfies certain requirements for the transmission angle. So, you may have other conditions that you impose on the design that cannot usually be dealt with in graphical synthesis. Graphical synthesis, you would have to, if you have other conditions like that, the only way to do it is you synthesize a linkage, you look at it, you analyze it, see if it meets your requirements, if not, go back. So, it is a trial and error process. Analytical methods are more difficult to set up, but they give you more power, more control over the design variables. So, that is what we will be looking at. So, when you want to have like an optimal 4 bar for a particular application based on these based on specifying the link length ratios or the transmission angle as I mentioned, then you want to explore analytical methods for synthesis, because they can help you cycle through, or they can help you put constraints on some of the design variables more easily. Okay. So, the instantaneous kinematic conditions is also a key reason why you might want to look at analytical linkage synthesis. So, the Chebyshev spacing, what we looked at would be sort of like the first step. If you know to determine your precision points, if you want to design a linkage, you would first analytically determine, and it is for a case where it satisfies the conditions for using Chebyshev spacing, that would be like the starting point for your design. You would determine the precision points using that. If it is a function generation, of course, it gets more complex if it is a motion generation or a path generation problem. But for motion generation and path generation, in many cases the application dictates, it is not so much the structural error, you are looking at specific points in the plane that you want to attain, specific points and orientations for your particular application, and then you design the linkage for that. You are not looking at the behavior over a range. Okay. The Chebyshev spacing applies when you want to minimize the structural error over a range, but if your application only demands that you have, that there are set positions that you want to attain, then you do not really need to go through that process. Okay. So, the basis that we will use in many cases, or one of the elegant ways of doing analytical linkage synthesis is through the use of complex numbers. Okay, I am sure all of you are familiar with using complex numbers in linkages. Okay. So, I will briefly show you how complex numbers can be used instead of vectors when you are looking at linkages. You can use, so for instance, instead of looking at this plane as the Cartesian xy plane, I can look at it as the complex plane where I have the real axis and the imaginary axis. So, this is my complex plane. It is just a different notation, it has certain advantages when it comes to working with linkages. Okay. So, if I look at a vector in this complex plane, I can write this vector r as x. So, if it has xr, yr, or let me just call this point P, or let us just call it A. Okay. So, if I want to, R A is X A plus I Y A. Okay. So, I have the real part, which is the part along the x axis. So, if this makes an angle theta with the x axis, X A is nothing but R A, where R A without the bar is the magnitude of that vector into cos theta, and the imaginary part is R A sin theta. So, this is R A cos theta plus I R A sin theta, where I as always as root of -1, but here we will use I as more of an operator. We are not really looking at it as that value, but you will see that we will use it as an operator for this application. So, if I look at, so let us say I have a vector, so let us say I have 4 vectors of equal length. Okay. We call this R A, R B, R C and R D. So, R A, so all these vectors have the same length, and let me call that R. Okay. So, I can write vector R A as just R. Okay. Vector R B would be I R. Vector R C is minus R, and R D is minus I R. Okay. So, I can also write this as minus R, I can write it as I square R, and minus I R I can write it as I cube R. So, if I look at this, multiplication by the operator I is rotating my vector by 90 degrees in the counterclockwise direction. So, the operator I in this notation, so each multiplication so this I can even write it in of, sorry, I'll write it as I R A, I square R A, I cube R A. So, each multiplication of vector R A by the operator I results in a counterclockwise rotation of R A by 90 degrees. The major advantage of using this notation is because of the Euler identity. So, I can write cos theta plus I sin theta is e power I theta using the Euler identity. Because I have e power plus minus I theta equal to cos theta plus I sin theta. So, when I differentiate this or integrate it, if I express it in the form e power I theta, d theta, e power I theta by d theta is I e power I theta, and similarly integrating it also gives me e power I theta by I. So, differentiating and integration, differentiation and integration become easy when I express it in this complex form, and we will see that when we do the kinematic, when we go to velocities and accelerations, it simplifies the math, and also you can relate it to the directions. Okay, it is easier to correlate with the vector directions, comparing displacement with velocity etc. becomes easier. So, this is the notation we will use for both analysis and for synthesis, because if you look at a 4 bar, I can express it as a vector loop equation. Okay, so I can say from this pivot to this pivot is one vector, this to this, okay, I can do that, or keep this, I will do this just to show you how the angles are measured. So, I can express a 4 bar linkage with a loop like this. Okay, I could potentially take R1 in this direction also, in which case if you look at this, as the linkage moves, okay, it always holds true. So, for the directions that I have taken, as the linkage moves, R1 plus R2 plus R3 plus R4 will be 0. Okay, you close the loop, because that is how you have assembled that is your kinematic chain. It is essentially saying it is a closed kinematic chain. Now, as the linkage moves, the values of R2, R3, R4 will change. The vectors R2, R3, R4 will change, because the angles that, so in this case how you measure the angles is, you will measure it from the root of the vector. So, this would be the angle of vector R1. R2 will be this angle, say theta 2. R3, theta 3, you will measure it like this, and for R4, so with the positive x axis counterclockwise, that is how you would describe the vector. Okay. R1 will be whatever its magnitude, maybe I will use small letters for e power I theta 1 in complex form. R2 will be R2 e power I theta 2, R3 is R3 e power I theta 3, R4 is theta 4. This would be the form. So, make sure you pay attention to how we measure these angles, always measured with the positive x or real axis, counterclockwise and measured at the root of the vector, at the tail of the vector, not the head. So, this is called the vector loop equation for a 4 bar. So, if I express it as these vectors in complex form, I have e power I theta 3 equal to plus r4 e power I theta 4 equal to 0. I do not necessarily have to take them in this directions. So, if I had r1 like I had it before, in this case r1 equals r2 plus r3 plus r4. This is also a valid way of, so depending on the directions of the vectors you would write the vector loop equation. So, this is the vector loop equation for a 4 bar, and we will use this equation for some methods of analytical synthesis. Let us look at one such method. Okay.